Assalamualaikum and a very good morning to Sir Hafiz Khalid and my fellow classmates. Today, our group will present about wave motion and sound. Okay, sound is a vibration that is transmitted in a medium that can be heard by a human ear. Human ears can hear anything between 20 and 20,000 Hz. Waves with a higher frequency are known as ultrasound. Those higher pitches are beyond human hearing. Meanwhile, sounds below human hearing are known as infrasound. Okay, so advantages of ultrasound energy used in medical diagnostic imaging. The first one is ultrasound can be directed in a beam. Ultrasound obeys the laws of refraction and refraction. Ultrasound energy is reflected off of a small objects. Ultrasound brings no injuries to health. Principal disadvantages of ultrasound. The first one, the energy propagates poorly through a gaseous medium. Ultrasound transducer must have airless contact with the body during examinations. The second one, ultrasound images are relatively noisy and have a poorer contrast than X-ray and MR modelites. Sound waves are also known as acoustic waves, as sound waves are coordinated vibrations. Molecules of medium capable of supporting the propagation of this wave. Sinusoidal sound wave is actually a series of areas of compression and rarefaction. Sine wave with the peak representing the pressure maximum and the valley representing the pressure minimum. The combination of one compression and one refraction represent one cycle. The distance between the peak of one compression to the next is the wavelength. To find the wavelength lambda m of the sound wave shown in figure 1 is by using the formula of lambda equal to 2 pi over k, whereas k is the wave number. Next, to find the velocity c meter per second, or the speed at which sound waves travel through a particular medium, is by using the formula of c equal to omega over k, or 2 pi f over k, where omega and f represent the frequency, radians per second, and hertz of the energy delivered to the tissue. To find the speed of sound in the medium, phase velocity is by using the formula of c equal to lambda of lambda f. The frequency and the wavelength are inversely related. The higher the frequency, the shorter the wavelength. To find the speed of sound in the medium depends on the average density, ρ0 kg per m cubed, and the compressibility, k m squared over n of the material or tissue in our case. The relationship is given by c equal to 1 over square root ρ0 k. It is a convenient way to express relevant tissue properties by using the characteristic or acoustic impedance Z kg over m squared s, which is defined by Z equal to ρ0 c.
Generation of ultrasound waves. Ultrasonic waves are generated by a transducer that includes a piezoelectric crystal that converts electrical energy, which is electric current, to mechanical energy, which is sound waves. These sound waves are reflected and returned to the transducer as echoes and are converted back to electrical signals by the same transducer or by a separate one. Piezo means pressure, so piezoelectric means that pressure is generated when electrical energy is applied to the crystal. Next, ultrasound is commonly used as a medical imaging modality as it became practical with the development of small piezoelectric crystal transducers. The sound waves is sent out in pulses that emitted 1 or 2 milliseconds of sound waves. The sound waves travel through the skin, chest, pericardium, myocardium, and etc. In the transition between each medium, a significant portion of all sound waves will be reflected back to the transducer. When the reflected sound waves hit the piezoelectric crystal, they begin to vibrate and create an electric current which is transmitted to the ultrasound machines for analysis.
Receiving ultrasound. So the backbone behind the theory of receiving ultrasound is the piezoelectric effect. So what does it mean by piezoelectric effect? It means by the ability of certain material to generate electric charge in response to applied stress. Meaning that there are certain material that can produce an electrical current when we apply a stress towards this material. So this material, we call it a piezoelectric crystal. Not only they can generate a charge, but when we apply a potential difference across this material, they can produce a vibration. So this is one of the unique characteristic of piezoelectric effect. It is reversible, meaning that it can vibrate and also receive a vibration that creates an electrical signal. So to put a simplest term, this piezoelectric crystal can convert from electrical energy to mechanical energy, which means that it will produce a vibration, and also mechanical energy back to electrical energy, meaning that they can convert the vibration into an electrical signal. Moving on the next slide, we are going to talk into a more technicality of the ultrasound system. Now, the main component of ultrasound system is a device called as a transducer, which contains an array of piezoelectric crystal. So inside this piezoelectric element, we have a crystal we call as quartz. So why we use these crystals is because it can change shape rapidly, meaning that they are easy to vibrate. So if they are easy to vibrate, which means that we can generate a high frequency with it. So when we apply a potential different or electrical signal to this crystal, we produce a high frequency sound wave pressure. We call it as an ultrasound. So when the ultrasound is directed to the body, it will pass through the skin and into the internal organ. As the wave encountered tissue or obstacle with different characteristic and density, it will reflected back to the piezoelectric crystal as echo. So the reflected ultrasound, we call it as echo. Now, when this echo is picked up by the piezoelectric crystal, it will convert the mechanical energy into an electrical signal. So the computer will process this electrical signal according to the strength of reflecting ultrasound and forming an image we call as sonogram. The process of transmit and receive cycle occurs in such a way the complete image is formed around 50 frames per second using a present technology. Now, one of the difficulties when dealing with ultrasound is the transmission. Now, the ultrasound is not a good conductor of less dense materials such as air. So when ultrasound travels through air, it will scatter and disperse, meaning that the reflected echo by the air molecule will be dispersed in compared to a denser material such as solid. And ideally, we could just seal the probe on the skin, but unfortunately, the skin surface is not entirely smooth. This results in many tiny pockets of air that will scatter the ultrasound signal and distort the image. So one of the solutions to overcome this difficulty is by applying a thick liquid between the probe and the patient's skin. So this thick liquid or the jelly will provide a cushion that directs the ultrasound towards the skin, towards the internal organ. So they will give a good sealant that will minimize the scattering due to tiny air pockets and allow a much clearer sonograph image.
Assalamualaikum, my name is Akid Haziq bin Norzeri. I will present my part about what happens to the ultrasound wave. Once the ultrasound enters the body, some of it returns to the probe to have the machine form an image and the rest is lost. When ultrasound enters the body, it partially undergoes attenuation, refraction, and reflection. When the body absorbs the energy of the ultrasound wave will be attenuated and cause the wave to disappear. This wave does not return to the probe, then it will be wasted. The more the body tissues the ultrasound wave have to cross, the more attenuation the wave suffer. That is one reason why it is more difficult to image deeper structures. Okay, what is attenuation? Attenuation is loss of energy, expressed as change in intensity as the energy travels through medium. Ultrasound intensity is measured in watts per square centimeter. To express the difference between ultrasound intensities, decibels were used. For example, when ultrasound becomes 100 times less intense, the attenuation is negative 20 decibels. When ultrasound is 1000 times less intense, the attenuation is negative 30 decibels. Rate of attenuation is called attenuation coefficient. For soft tissue, the attenuation coefficient is half the frequency per centimeter. For example, an 8 MHz signal will lose 4 dB per centimeter of travel. Okay, based on the diagram above, every substance such as nerve, muscle, or fat has a unique property called acoustic impedance. This one. Acoustic impedance depends on the density of the substance and the speed of ultrasound in that substance. Substance with different acoustic impedance alter the course of ultrasound wave in an important manner. The picture above shows what happens when ultrasound wave try to flow from one material to another material with different acoustic impedance. The ultrasound wave refers to red arrow. Part of the ultrasound wave goes directly into the second material but becomes slightly bent away from their original direction, referred to pink arrow. This one. The bending that occurs when ultrasound moves from one material to another with different acoustic impedance is called refraction. Part of the wave reflected the back of the probe is shown as a blue arrow in the picture. The amount reflected depends on the difference of the acoustic impedance between the two materials. The more the difference, the more the reflection. Reflected waves are very important because only these waves return to the probe and provide information to the machine to show the picture. Based on the picture above, as the ultrasound wave crosses from one tissue to another, each with a different acoustic impedance, the part of the wave is reflected back at each intersection, referring to two blue arrows. Thus, multiple reflected waves return to the probe, and the machine uses the information to display image showing various tissues. Object irregular surface, such as the nerve, ultrasound wave propagate in all directions, referring to blue arrow in the picture above. It shows a small portion of wave reflected back to the probe. This is called diffuse reflection. When there is large and smooth object, such as a nerve blocking needle, as shown in the diagram above, this will cause the ultrasound wave to be reflected. This is very useful because it helps us to see the needle clearly while doing a nerve block that is completely guided by ultrasound. This mirror-like reflection, where the waves are reflected mostly in one direction, is officially called specular reflection.
Okay, so next is ultrasound mode scanning, which we have A mode scanning and also B mode scanning. So the A mode is the simplest form of ultrasound imaging and is not frequently used. The ultrasound wave that comes out of the probe travels in a narrow pencil like a straight path, and one use of the A scan is to measure length. For instance, ophthalmologists can use it to measure the diameter of the eyeball or the length of the tumor in the eyeball. So here I have a very simple version of an ultrasound. We have a normal eyeball here. And what are we going to do now is we are going to draw the graph that will gonna appear on the screen, but I already draw the graph. Okay, so how are we getting this kind of graph? Okay, so an ultrasound wave is sent from the probe, and at the same time we are gonna have a straight horizontal line from the left of the screen, and the line moves horizontally measuring times, and as the wave reaches the first wall of the eye, some of the ultrasound is reflected back into the probe and some is transmitted into the eyeball. So the reflected wave here is recorded as a bump or like a spike. The stronger the reflected wave, the higher the height of the bump. So the height of the bump is called amplitude, which is what the A of A mode scanning stands for. So how are we going to know either the reflected wave will be strong or not is by their acoustic impedance of the two materials at the boundary. And as the ultrasound gets to the back of the retina, okay, the reflected wave would be much stronger because there is variance in density, since the back of the retina has like sclera and choroid have much density than the lens. Therefore, the reflected wave would be stronger and the bump would be higher. So we already see the graph represent for this eyeball. So we can get information from the graph, which are the time difference between the first bump and the second bump represent how long the ultrasound wave took to travel between the two walls. Okay, so the longer the length, the longer is the time difference. So if we know the time difference, then we can calculate how far the wave travel from the two walls of the eye, giving us the eyeball length. Okay, so here are my explanation that I have just explained to you. Okay, so next we have B mode scanning. So the B mode scanning is very similar to the A scan mode, and just like the A scan, a wave of ultrasound is sent out in a pencil-like narrow path, and the horizontal line represents the time since the wave was released. So let's start with the picture A first, and I'm still using the same example, which is the eyeball. So when the wave meets the first wall, a part of the wave is reflected back into the probe, and instead of a bump, the strength of the reflected wave is recorded by a bright dot. So the brightness of the dot represents the strength of the reflected wave. The brighter the dot, the stronger the reflected wave. So that's why the letter B of B scan represent for brightness. Okay, so as the wave continues until at the back of the eyeball, so some of the ultrasound is reflected back into the probe, and the reflected wave is represented as a bright dot on a screen. So if a B scan is done at different level of the object, we will get two-dimensional image on the screen. Okay, so first a B scan is done at the top of the structure chosen. Okay, so the first B scan line is kept on the screen. Then at slightly different level, the B scan is repeated. So the B scan results is also kept on the screen. Then again, at a slightly different level, the B scan is repeated. So in this way, a 2D image of the object is formed on the screen. But in real life, the process happens very, very quickly. The structure are scanned and the image redrawn many times a second. So the complete description of the mode is real-time 2D B scan. So the 2D refers to the fact that the image has two axes, two-dimensional, which is y-axis and also x-axis.
Okay, next is prop selection. Props are generally described by the size and shape of their face. Selecting the right prop for the situation is essential to get good image. There are three basic types of prop used in emergency and critical, which are linear, curvilinear, and phase array. Firstly, linear props, also called as vascular prop, generally have high frequency, better for imaging superficial structures and vessels, and also generate rectangular image on the screen. Secondly, for the curvilinear props, it has wider footprint and lower frequency for transabdominal imaging, high frequency for endocavity imaging, and also generate pie-shaped image. And lastly, for the phase array props, generate an image from electronically straight beam in a closed array, generate image that comes from a point, and lastly, generate a pie-shaped image. Next, we continue with straight linear array. This prop is designed for superficial imaging. The crystals are aligned in a linear fashion within a flat head and produce sound wave in a straight line. This prop has higher frequencies in range between 5 until 30 MHz, which provides better resolution and less penetration. The image produced is rectangular in shape, and this prop is commonly used for vascular access, evaluate for deep venous thrombosis, appendicitis in thin patient, and lastly for skin and soft tissue for abscess for rich body. Next, we continue with curvilinear array. This curvilinear array or convex prop is used for scanning deeper structure. The crystals are aligned along a curved surface and cause a fanning out of the beam. This prop have frequencies ranging between 1 to 8 MHz, which allows for greater penetration but less resolution. The image generated is sector shape. This prop is commonly used for abdominal aorta, kidney and bladder evaluation, abdominal portion or fast exam, and lastly for transabdominal pelvic evaluation. Okay, next, intercavitary array. It has a curved face and it also has high frequency which is 8 to 30 MHz than the curvilinear probe. The curved face creates a wide field of view of almost 180 degrees and its high frequency provides superior resolution. This probe's elongated shape allows it to be inserted close to the anatomy being evaluated. It is commonly used for gynecological applications, but can also be used for intraoral evaluation of pertonsillar abscesses. Okay, next is phase array. It has frequencies between 2 and 8 MHz. It functions at low frequencies which is useful for viewing the abdomen, pelvis, and for procedural guidance. It is used for echodiography, chest ultrasound, and even abdominal ultrasound. It provides a broad depth of field with a small footprint, allowing the sonographer to view deep structures through a small acoustic window such as between the ribs. This probe can be used in procedures such as cardiac imaging, imaging between ribs in the flank or right upper quadrant, and it also may be used for transabdominal imaging if curvilinear probe not available. Okay, that's all from us. Thanks for watching.